astronomical texts is the Surya Siddhanta. We don't know exactly when it was written, probably in the 4th or 5th century AD. It's possible it was written even earlier than that. But already here in this first Indian astronomical work that uses trigonometry, we see that the Greek chord has been replaced by the half chord, what would come in the West eventually to be called the sine. And there actually is an interesting story behind how we got this word sine. The Indian astronomers quite naturally called it a half chord. The word for chord is jia and half is ardha, so this was an ardha jia, a half chord. Although eventually they dropped the adjective half, they just referred to it as a jia or jiva. And this meant, though, the half chord. And from jiva, the word was taken up by the Islamic astronomers, and they pronounced it as jiba, and they wrote it in Arabic, which only uses consonants, as JB. And when the first Western astronomers were trying to figure out what this function was that was being described, they looked at these Arabic letters JB, which of course did not represent any word in Arabic. Jiba is not an Arabic word, it's simply a transliteration of the Sanskrit word for this half chord. They looked at those letters JB, and the one Arabic word that they knew that used the letters JB was jaib, which means breast. And so they assumed that this was to be called a breast. Now, it's not quite clear how this happened, but perhaps out of excessive modesty, rather than calling it a breast, they decided to refer to the fold of a cloth that might cover a breast, and the fold of a cloth could be referred to as a sinus. And so this became a sinus in Latin, which in English eventually would become our sine. So we get sine out of a mistranslation of a transliteration of a Sanskrit word. The Indian astronomers also studied the cosine, which was the kotijia. And if you think about the bow and arrow, so we've got the arc of the bow, we've got the chord, and we've got the arrow. The shaft of the arrow, so that's the distance from the center of the circle to the chord, that is the cosine, or the kotijia. And the Indian astronomers also made great use of the ukramajya, and that's the tip of the arrow. That's the little part of the arrow between the chord and the arc of the bow. This would come to be called in English the versed sign. We no longer work with the versed sign. The versed sign, after all, is just the radius minus the cosine, so there's no real need to come up with a separate term for this. But if you look in the 17th century, something like Newton's Principia, his mathematical principles of natural philosophy, he does a lot with the versed sign, and this is where it's coming from. It's an Indian invention, and it comes out of describing that arc, that tip of the arrow. I'd like to spend some time now looking at the trigonometric tables that people came up with, and particularly the work of Aryabhata. Aryabhata, as I said, was born 476. He was in the Gupta Empire. The Gupta Empire had begun around 320, would last until about 600 AD. Aryabhata lived in Kusumapura, which was the center for astronomical work, very near the capital of Pataliputra, which today is modern Putna, in India. He also was working with a circle of radius 3,438. And he almost certainly was not aware of Ptolemy's Almagest, because, as I said, Ptolemy's Almagest was actually able to look at chord lengths for arcs all the way down to half a degree. And Aryabhata was working with chord lengths of 3 degrees 45 minutes. In other words, what he was doing was starting with a chord length for 60 degrees, and then from that you can get the chord length for 30, 15, 7.5, and then 3 3/4 just by taking half angles. So he had a much rougher table. But he did something that was extremely important. He was looking at the problem of interpolation. If you've got a table of values and you want to find some intermediate value, how do you go about doing that? Well, a natural way of doing this interpolation is that if you've got a value, say, that's halfway between the two given values, you just take the output that's halfway between the two outputs. And rather than looking at the actual trigonometric table that Aryabhata was looking at, I'm going to show you a somewhat simplified table that illustrates the point of what Aryabhata and the later Indian astronomers were able to do. So what I'm going to do, on one side, I've got inputs that are the digits 1, 2, 3, and 4. And then I've got outputs that are the digits 1, 3, 7, and 13. And the question then is, if I've got an input of 2.5, what should be my output? Well, 2.5 is halfway between 2 and 3, so that suggests that my output should be halfway between 3 and 7. And so we might take 5 as the logical output, and that's what's called a linear interpolation. We're just assuming that things work as if they're on a straight line. But in fact, if you look at these output values, 1, 3, 7, 13, you see that the output values are increasing. 1 to 3 is a difference of 2, 3 to 7 is a difference of 4, 7 to 13 is a difference of 6. These differences are themselves increasing. Aryabhata did not just look at the differences, he actually took a table of the second differences. And he used that to refine the way in which he was going to do this interpolation. What is happening in this table is that as we move further down the table, the increase gets bigger. And so the increase in the output going from 2 to 2.5 should not be as big as the increase in output as we go from 2.5 down to 3. We need a bigger increase in output. Now, the total increase in output from 2 to 3 has got to be 4. So the output increases from an output of 3 to an output of 7. But how do we then arrange this output in order to take into account the fact that the outputs are increasing at an increasing rate? And one of the things that you can do is to decide that from 1 to 1.5, we've got to have a certain increase in the output. From 1.5 to 2, we've got to have a greater increase in the output. And the increase in the output has to increase by the same amount each time.